Yeah. So for Rice's theorem part 1, do you remember what it states?
And so, non-trivial property is decidable.
Yes. For non-trivial property, it is not decidable. So now if I ask for so firstly, what does it mean? What do you mean by properties of two recursively enumerable languages? Firstly, we need to ensure that. So let me just write two recursively enumerable languages. Let me say L1, L2. Okay, so and this can also be written as, let's say, M1 hash M2, such that L of M1 is equal to L1 and L of M2 is equal to L2. Now, a property for property for two things will basically be recursively enumerable cross recursively enumerable going to true or false. So what is a trivial property here then?
All are true or all are false.
Yeah, so that means that all true. Let me just write it formally. For all L1, L2 in RE, P of L1, L2 is equal to true. And the second one is for all L1, L2 in RE, P of L1, L2 is equal to false. Okay, so anything other than this is a non-trivial property for pairs of languages. Now, the statement we want to prove is that any non-trivial property of pairs of RE languages is undecidable. And for that, what we have to show is look at the problem. So let me write it as M1 hash M2 such that the property of first language and the second language being true. Let's look at this. Let's look at this set. This is not recursive. So how will you show this? What strategy are you thinking of using?
Ma'am, some reduction from complement of HP.
Complement? Why complement?
Oh, ma'am, it's not recursive. Ma'am,
Not
then
recursive. Yeah, we are just
if
proving the
we
first part. Okay. So suppose you are trying to show this. Okay. So that means you take some m hash x, and this goes to some m1 hash m2, and this is, yeah, okay. So what do you want from this m1 hash m2? What do you want from m1 hash m2? You
Property
want
of
something.
language of M1, comma language of M2 is true if and only if the M halts on X.
Correct. And we can also assume, since this is a non-trivial property, we can also assume, let's say without loss of generality, that property of phi is equal to false, and property of some, um, let's say a b, is equal to true. And of course, if if I mean, this is without loss of generality, because otherwise I will just be giving a reduction from not of HP to the problem, which actually shows not recursively enumerable for that particular property. But in particular, it's also not recursive. Okay, now can you? So I also know that this A and B, let's say A is equal to L of some Turing machine N1, and B is equal to L of some machine N2. Okay, now
So, ma'am, we can take in the input V of this V1 and V2 of these Turing machines, and then we can,
so
if the simulation
inputs,
of,
let's say V1 of M1 and V2 of M2. Okay, now what are you doing?
ma'am, so if the simulation of, so we first we then simulate X M on X, and then if the simulation halts, we simulate V1 and V2 on V1 on M and V2 on M in a time sharing manner.
If N1 accepts, then accept and hold. And this is also same. M2 simulate M on X. If false, simulate N2 on V2. If N2 accepts, accept and hold. Okay. So now what's the conclusion? So if M halts on X, then L of M1,
Is equal to L of N1 equal to A.
and this means that property of L of M1, L of M2 is equal to true. And if M doesn't halt on X, then L of M1 equal to L of M2 is equal to phi. So the property of L of M1, L of M2 is equal to false. And therefore we are done. And as I said, if this was the opposite way around, then we would have to give a reduction from not of HP. Okay, so uh, now second question is, now we can work on pairs of recursively enumerable languages. So prove that M hash n such that L of m is equal to L of n. This set is not recursive. And you also have to prove that I mean, you have to determine whether it's recursively enumerable or not. Okay, so one hint that see, we have seen certain kinds of reductions, and we know that if I just do this basic simulation of if m halts, then I accept whatever string I'm getting as input, and if m does not halt, then I mean, anyway, I don't have anything much to do. Then I know that there is a separation between sigma star and phi. So if m halts, then I'm going to get sigma star as my language, and if m does not halt, then I'm going to get, I won't be accepting anything. Similarly, another sort of framework is if if I want to get if I want to determine, let's say, if I may be using m, first I simulate m, and then I simulate some other language, the machine for some other language. So if m halts, then I'm going to get that other language, and if m doesn't halt, then I'm going to get phi. So we have certain frameworks. So now, can you use
Ma'am,
one of those frameworks? Huh.
ma'am, if M0 is a total Turing machine that accepts the language 5, and then we can just take a reduction from the halting problem to this problem. So if M hash
So
W is,
I'll just call it phi. Yeah, please continue.
yes, ma'am. So if M hash X is the input for the halting, the is the instance for a halting problem, then we can
Huh.
make a reduction. So we will output n cross n hash n m naughts, where m naught is a known Turing machine with the language phi, and then we can just simulate the same way we did, such that language is sigma star if m halts on x and phi if m moves on x.
Okay. So this n you are this is where you are simulating m as a subroutine, right?
Yes, ma'am.
Okay. Yeah.
And so if m halts on x, then we accept everything. Otherwise, we don't.
Um, but we want. I think you are giving a reduction from. Don't you? Do you want phi or sigma star here and not? Because if m halts, then you're going to get everything, right? If m halts on x, then you're going to be accepting everything. So n naught should be accepting sigma star, right?
Yes, ma'am. Yes, ma'am.
Okay. Can you just give me 1 minute? Yes. Okay. So this is first one. So another thing that I want you to observe is, can you use Rice's theorem here? Can you hear me?
Yes, ma'am, you're audible.
Okay. Can you use Rice's theorem? So what do you have to show in order? So we basically have a pair of languages. So I mean, you if you can show part one for pairs of RE, then I'm done, right? So if you show that this uh, like property pi, I'll say property pi is non-trivial, then I should be done, right? From what we proved before.
Yes, ma'am. We can take the equality property and it's non-trivial.
Right, right. Okay. So now let's move on to part B. Is this language recursively enumerable?
Ma'am, with the N0 accepting phi, I think does it make a reduction from HP complement to pi and hence it's not recursively enumerable?
Um, there is still, even in the previous thing, there is one step left, right? In HP complement, if I just simply did, I mean, I won't, okay, let's see. HP complement, you're saying M hash X goes to N hash N naught. And N is just simulating M on X. Okay. And N naught is accepting phi. L of N naught is equal to phi. Now, if M falls on X, then what I get is sigma star. And if M doesn't hold, yeah, I think you're right. N is equal to phi. Yeah. Okay. So now let's go to the third question. So now your set of languages is or your set of languages is the strings corresponding to Turing machines whose languages are context free. So now using Rice's theorem, can you prove that neither CFL nor its complement is recursively enumerable?
Ma'am, we can just prove that neither CFL nor its complement is non-monotonic, so we can take the uh,
Can you
lang-
give an what you say? Yeah, correct. Okay, but so basically you want to use part two, and why are you saying neither of them are non-monotonic?
and because if let's say we consider the language A power n, B power n, then for the property that a language is context free,
You mean you mean A par n, B par n, C par n, right?
yes, ma'am, yes, ma'am. Correct.
Okay. Hmm?
Yes, ma'am. So if we want to use the property that the language is context free, then we
Hmm.
say that phi is a context free language, but
Correct.
eparen, viparen, ciparen is not. So it's not monotonic.
Huh.
And
Huh.
for not
So
context free
this
language,
shows non-monotonicity for CFL.
and
And
for
then
the complement of CFL, we can take a power n, b power n, c power n is a subset of sigma star.
correct, correct. So this is not CFL and this is CFL. And this shows non-monotonicity for complement of CFL. Okay, good. So can you prove it without Rice's theorem now? So I mean, we will take our favorite problem, right? HP to CFL, and then I have to reduce HP to not of CFL. So let's do these two reductions. Or you can change the starting problem. Sorry, not HP, not of HP. Yeah.
Then we can use this reduction from HP to a Turing machine N such that uh, the language of N is context free if and only if M does not halt on. The language of M is not context free if and only if it does halt on.
Okay. So 1 minute. So you're going M hash X to N such that L of N
Is context
not
free.
CFL. Huh?
Yes, ma'am. If L of N is not CFL, if M halts on X.
Not CFL if M halts on X. Okay.
Yes, ma'am. Then we can just simulate M on X, and if the simulation does not halt, it is the language is fine. Otherwise, if the simulation halts, we run another total Turing machine that accepts A power n, B power n, C power n.
Okay. So simulate an M on X. If halts, then accept input Y. So this is N. Okay. And halt. Okay. So M halts on X implies that L of N. No. So you had another cell.
Yes, ma'am. Y.
Sorry. Huh. If halts, then you're saying simulate, or I'll just brevity. I'll just say check if Y belongs to uh like some L which is not CFL. So let me say example L is equal to A to the N, B to the N, C to the N. Okay, so now if M and then if accept. Okay, now if M halts on X, then you get the language L of N is equal to L, and M does not halt, then you get the language phi, and this is CFL and this is not CFL. Okay. Okay, so now what about this? Not of HP. So you want that m hash x reduces to some n such that m uh, does not halt on x if and only if L of n is not CFL, right? So previously we were showing if m halts, then it is not a CFL. So definitely you cannot map does not halt to phi or sigma star or something like that. You have to, so if it does not halt, you have to detect it. Somehow you have to detect it also, because if it does not halt, somewhere, I mean, you can't keep simulating. Somehow you have to detect that it's not halting. And if it does not halt, then you accept not as not CFL language.
Ma'am, we can make another Turing machine n, which on input v checks if it is of the form a power n, b power n, c power n, and if it is not of the form, it rejects immediately.
Mm-hmm.
And if it is of the form, then we can determine the value of n and then simulate m on x for n steps, and if it stops by n steps, then we reject uh, p, otherwise we accept.
Okay, so you simulate m on x if stops, sorry, if halts, if halts, then you are rejecting.
Yes, ma'am.
Otherwise, accept. Okay, so for this, m does not halt. So that means if m does not halt, then you are accepting everything, right?
Yes,
Sorry, you are accepting a power n, b power n, c power n.
yes, ma'am.
Okay, so if m halts, so let's say in s steps, then what happens?
We are just accepting a power n, b power n, c power n greater than equal to 0, n less than s, which is a finite set.
0, correct. So this is a finite set. So therefore, it is a context-free language, and this is not context-free. Okay, good. Okay, so I think we are in the last question. So let M be a Turing machine. Is it decidable whether Lm is equal to Lm reverse? So the problem is M such that so the question is it recursive?
Ma'am, we can use the previous to previous reduction such that the language is A power n, B power n, C power f, and if m halts on
Yes,
x,
ma'am. We can do that, and we can show that it is non-monotonic as well.
Okay. Okay, so let's do, you said two things. So first thing you're saying, you take language A power n, B power n, C power n greater than equal to 0, and then
ma'am, then this
okay.
language is not equal to its
So
reverse.
do previous reduction. Right. To show not recursive. But somebody said something about not being monotone. I think you mean not being trivial, right?
I mean, ma'am, this is a subset of sigma star, and sigma star is like if we reverse that, we get the same thing.
Hmm.
So this is not
But
monotonic, right?
I don't think your arguments are correct. You just see monotone. First of all, we are looking for whether this is a decidable property or not. So monotonicity comes if we are looking for whether it is semi-decidable. But even the statement that you made, whether it's monotone or not, because sigma star is, uh, it's always going to be true for sigma star. That's not enough, right? You have to show for any pair, any sets A and B. If A is true, then B must be true. So look at previous example.
That's a
That
non-monotone.
not
Like
CF.
for phi it is true, and for this it a power and b power and c power it is false.
Once more.
For phi it is true,
Uh,
and for a power and b power and c power it is false.
okay.
So this
So
shows
you have
non.
shown, but then what have you shown? It
Like
shows not. This is a.
this will eventually go to like not
Oh, okay.
recursive,
This will. Yeah, exactly.
not even
So
semi-decidable.
actually, you have shown that the property is non-monotone. Yeah. So this actually shows that. I mean, this also shows that it is. Let me just rewrite it again. So first thing that you show is this is non-trivial, and second you show that it's non-monotone. So therefore, what we can conclude it is it's not even semi-decidable. So that was actually my second part of the question: is it semi-decidable? But can you give an explicit reduction for this part, for whether it's semi-decidable or not?
Ma'am, we can use the reduction
No.
A power n, B power n, C power n if m
Yeah.
halts on x. Otherwise, if m does
So
not.
I'll just write similar as question 3 using uh, A power n, B power n, C power n decider or no recognizer as subroutine. Okay, so those are the questions I had.
Ma'am,
Yes.
ma'am, in the question 3 part, ma'am, both the languages are don't hold this property of lm equals lm reverse. Ma'am, both the decided what?
LM equals LM, this part, this thing.
Yes, ma'am. In question 3 part B, we were taking a n, b n, c n, and a finite subset of them.
Question 3. Question 3, right? Yeah. So for how will what about if I give you a finite set of strings? Can you show that it is a CFL? So I'm giving let L is
No,
a
ma'am, I'm not talking about CFL. I'm talking about L of M is equal to L of M reverse. That one.
once more L. Are you talking about this question or something else?
Yes, ma'am. Question 4, where we are using question 4 part B, where we are using question 3 as a subject.
This part.
Yes, ma'am. Yes, ma'am. So, ma'am, here exactly what we are doing.
Okay. Let me see. Right. You're right. So we yeah. This is not the reduction. Okay. So let's try for this reduction. So we okay. So we have this going to pi and m hash x doesn't hold if and only if uh, some n has L of n equal to L of n reverse. So if it does hold, then we should land in a language that is not a reverse of itself.
Okay, ma'am. So here we can use the part A. Yes, ma'am.
Can you do it once more? So you're saying I'm going to show m hash x holds if and only if n is such that L of n not equal to L of n reverse, right?
Yes, ma'am. So, ma'am, if it holds, then we accept A power n, B power n, C power n.
So if m holds, then run machine for A power n, B power n, C power n, accept and hold if it accepts. Otherwise, no, I don't. I think there's still some problem, right? Yeah. No. This is fine. This is fine. Yeah. So m m doesn't hold implies L of n is equal to phi. So this is equality, and m holds implies L of n is equal to A power n, B power n, C power n. So this is non-equality. Okay, so this reduction itself shows that it is not semi-decidable, not decidable. Okay, so I'm done. Then today was the last class. Uh, I think after this, I think our exam is scheduled for the 12th, right?
Yes, ma'am.
Okay, so those of you who have opted to come for the physical exam or who have not given any options, Um, so those who have, especially who have not given any options, please let us know um, whether you have explicit choices or not. Otherwise, all of you have to. We will give you a classroom. We will assign a classroom to you. All of you have to come to that classroom, and we'll hand out the question papers to you. All laptops, books, online material, everything is open for you, as is for everybody appearing online. Yeah, that's all. You can bring all laptops, books, everything. You can bring everything. It's an open book test. Okay, then if there are no other questions, then we can stop the meeting. Okay, thank you.